in ER diagram, it's nice. And I think that's the way to because this has an aggregation. It's relating these two things coming out in this
Hello.
The mic works. I don't know. I didn't. Thinking about the tables is natural. This is kind of a natural way to sound because you know, like objects, tables, objects. This is dry.
Okay. All right, let's get started. So first of all, I made an announcement last Wednesday. I sent a reminder again on Canvas. Basically, the homework is supposed to be due today, but because we didn't have time to cover the discussion on ER, converting ER to relation models, so we give an extension to that. The new due date for homework 1 will be on Wednesday. And with that said, yeah.
Will we do a class here?
Yes, you're going to be due here. I think I mentioned, I sent an announcement regarding how you submit your written homework assignment in Canvas. I don't know whether all of you paid attention to that, but let me just make it clear what's the drill for submitting your homework. Okay? First of all, we do not accept electronic submissions because we have a fairly large class, and if you start sending electronic submission to us, and we need to print out for you, and it quickly become, logistically speaking, it becomes infeasible for us to do that. So you need to turn in physical copies of your written assignment. Whether you do that using pen and pencil, paper, or you do it electronically, then later on you print it, all of those will be fine, but you need to submit a physical copy of your written assignment. Which means on Wednesday, unless otherwise specified, the homework will be due at the beginning of the lecture on the due date. So on Wednesday's lecture, you will submit your written homework assignment right here on this desk. If you have multiple pages, which I expect that's the case for homework 1, you need to stable them. With your name and UID written on the first page. Okay. Any question regarding the submission of your homework 1? Yeah.
So just to clarify, so it is okay if it's handwritten?
Yeah, totally okay. Yeah. As long as you make sure your handwritten is, clear and legible. Any other questions? Okay. Without any further questions, let's move on. So I'm gonna fast forward a little bit. We still have a few things from lecture 2 slides that I haven't discussed, but I will skip those and discuss the conversion from ER to relational mapping first. Then we will go back and cover those. A quick recap what we said on Wednesday's lecture. We talked about the concept of super key, the concept of key, and under key we talk about primary key and candidate key. And then we also talk about foreign key. It's interesting, in technology people call this foreign key instead of alien key. Right? I mentioned that because as an immigrant, so when I fill up my paperwork, right, to the immigration office. So for the first time, I realized I'm an alien. Right? So instead of call you foreigners, they call you aliens, right? Alien resident. So I'm an alien resident. So I was wondering why people don't call this alien key instead of foreign. Okay. All right. Okay, so for this class, if you decide to call this alien key, that's totally fine. Okay. All right, so we talk about super key, the concept key, and foreign key. A quick recap. Super key is a set of attributes from your schema, and no two records from the instance of that schema should have the same values on all key attributes. Okay? When those conditions are met, we say that's a super key. That's a super key. What about the concept key? First of all, it's a super key. So the concept key is recursively defined using the concept super key. So first of all, it is a super key. The second requirement is any proper subset of a key cannot be another super key. Any proper subset of a key cannot be another super key. Okay? And you may have multiple keys for a given schema, and we will choose one of them as the primary key for your schema, and the remaining ones, the remaining keys will automatically become your candidate keys. Foreign key. If an attribute or a set of attributes in one table is a key from another table, then this attribute or this set of attributes on the first table is called a foreign key that references to the second table where this attribute or this set of attributes serves as a key. Okay? So these are some fairly important concepts you need to make a note for. Right? You need to understand this really well. Okay? So with that being said, let's turn our attention to how to convert your ER design to a relational model design. Okay? Because ultimately, your database management system does not understand your ER diagram, right? Your database management system understands tables, schema, and instance of your schema. So we need to turn your design into relational tables. So let's start with the basics, right? ER model, the basics of ER model, as we recall, consists of entity set and relationship set. Right? That's where the name comes from. ER stands for entity set and then relationship set. So let's first look at how we convert entity set into relational tables. Look at this example. We have an employees entity set where SSN is the key for this entity set. And how do I go from here to here? Well, very simple. The rule of thumb is every single entity set in your ER design will go into a corresponding relational table. So every entity set will produce a relational table for you in this conversion process. When you try to convert your ER diagram to a relational model design, every entity set will give you a relational table. And the relational table name, you can use any name of your choice, but to be consistent in your design, it's recommended you simply use the name of your entity set as the name for that corresponding table. Okay? And every single attribute in your entity set will go into the schema of your relational table with the same name and same attribute type. The attribute type is also known as the domain of an attribute, right? The domain of an attribute. And that basically tells you the possible values that attribute may take. And lastly, you do need to, for every single relational table, you need to have a primary key. You need to specify at least the primary key. And by default, the primary key of your relational table that comes from entity set is simply the key of that entity set. So in this case, the key of the entity set is SSN, so that the primary key of the corresponding table will be SSN as well. Okay? So the first part is really trivial, right? Just remember this. Every single entity set goes to a relational table. What about relationship sets? The discussion here is a little bit more involved. The reason for that is, if you recall the discussion from ER design, we have different types of relationship sets. We have different types of relationship sets. We have which is a many to many many. Right? We also talk about one to many many. So I'm going to ask one of you to tell me, obviously this is the one to many mapping, but which is the one side, which is the many side? Okay? Yes?
Left side is the many, right side is one.
Say again?
Left side is many, right side is one.
Oh, I was on. Okay, anyway, go ahead. Yeah. So say again, sorry?
Left side is many, right side is one.
Very good. What's your name?
Steven.
Sorry?
Steven.
Stevens. Okay, left side is many, right side is one. Remember this? The error comes out from the many side. The error comes out from the many side. Okay? And then lastly, we also have a one-to-one map. Right? One-to-one map. This is in addition to, additionally, you may have participation constraint. A participation constraint is indicated by using a bold line in your design, right? I may bold this, and that indicates total participation constraint on the right-hand side. Okay? The challenge really is how are you going to capture all of this when you convert a relationship set to a relational table. Okay? So let's start from the simplest case, right? Or the most general case as well, which is many to many without total participation constraint, right? That's the most general case that you will encounter in a relationship set. So the way you convert this is as follows. You actually, once you understand what's going on, it actually makes total sense. Okay. So if we try to capture this many-to-many relationship set, and what's really going on? Well, you're going to have two. Suppose we're talking about, unless otherwise specified, by default, we always talk about binary relationship set, right? So there are two entity sets involved in this relationship set. I'll give you a simple example. This is employee, this is department. Suppose this is works for, right? So let me add the entity set to make it super clear. So employees work for department, and it's many-to-many mapping because an employee may work for multiple departments, and department obviously may have multiple employees in that department. And that relationship set essentially captures these lines going across these two entity sets. Right? The collection of these lines form that relationship set. And obviously, if you try to convert this into a table, intuitively, every single line here becomes a record in your instance for that relationship set table. You follow me? Imagine you have a relational table for this relationship set. Then every single line here is a record in the instance of that relational table. Right? Okay? The challenge is how do you, as required by the relational model, every two records in an instance of a relational table must be distinct from each other. You cannot have duplicated records in a relational model. In other words, all we need to do is to what? Is to be able to uniquely identify every single line from this relationship set. And how do we uniquely identify a single line? Well, this line is identified by the two participating entities. Another line is identified by the other two participating entities. So how do you uniquely identify a line? Well, it is by looking at the two participating entities for that line. So the question then boils down to, how do you identify these two participating entities? Well, by their keys. So the key of employee will be SSN. The key for department will be, let's assume that's DID. You follow me? So suppose the SSN value for this guy is SSN1, and this is SSN2, and this is department 1, this is department 2. So how do you identify this right here? Well, right, using the keys of the two participating entities, you will be uniquely identify this line right here. What about this line? Well, that's simply, that will identify this line right here. Do you follow me? Do all of you follow me on this? The point is, yes, you can identify this line by the two participating entities, but you do not have to copy all the attributes of those two entities in order to identify this line. All you need are their keys. You don't need the rest of their attributes. Because when you do that, you are duplicating information in your database. The other attributes of those two participating entities are already captured where? Well, are already captured in a department table and in an employee table, respectively. You don't have to, and you don't want to, duplicate those attributes over. So for this works for relationship set, it will give you a works for table, and the schema of this table will be, per our discussion, the schema of this table will be the keys from the two participating entities, which is SSN and DID. What other attributes you may want to have in the work for table? Well, any additional attributes you may have introduced in your design to this relationship set. For example, I may ask for the start date that you worked for a particular department. And this is the attribute that's specific towards this relationship set, meaning every single line here would have a date. For example, January 1, 2010. This would be July 1, 2015, so on and so forth. So every single line will have a specific value for that attribute, and you need to capture that. And you cannot capture this in the employee table, you cannot capture this in the department table. The best way to capture that is in the work for table itself. So you will have another attribute like start date for that attribute. Okay?
Sorry, Feifei. I have a question. So just to go off that example of employee it works for, let's say there is a field that's like a rating of that employee that's for the time you worked in that department.
Yep.
So there could be multiple times that employee worked in that department, right? So there needs to be a way to have instances of the time it worked. So which leads me to think that you can't use SSN and department ID as the primary key for that relationship. Is the best practice to create an instance ID and use that as the unique identifier?
Okay, So there's a couple of things. I think I called your name last lecture, Eric or something?
Daniel.
Daniel, yes. Okay, Daniel. Okay, Daniel mentioned some really good point. I want to clarify one by one what he said. He said a couple of things, right? First of all, he mentioned it's possible that the employee may work multiple time instances for that department, right? You know, so if that's the case, it is not what I'm gonna say next is really important, right? That is orthogonal to how you convert your ER design to the relation model. That goes back to your ER design itself. If you want to capture the fact that the employee may work for the same department for multiple different durations, and we actually had a discussion on this regarding the ER design. The best way for that is to introduce a duration entity set and have a ternary relationship set between employee, department, and duration to capture the fact that the same employee may work for the same department in multiple different time periods. The reason for that is if you design it like this in ER diagram, as we argued before, for the same relationship set, the two entities can only participate in the same relationship set once. In other words, there should be only one line connecting two entities. You cannot have another line, yet another line, try to connect them. That will not allowed in ER design. That's not allowed in ER design. So if you try to capture the fact that one employee may work for the same department multiple times, what you should do we have a discussion on this. This is the discussion we had before, right? So, which is if you want to capture the fact that employee works for the same department multiple different instances, then you need to introduce another entity set, and then having a ternary relation set among them. So, for Daniel's question, his question is really about the design, refinement of your design, rather than on the converting of your ER to relation model. Does that make sense to you? Once your design is fixed, the way to convert your ER diagram to relation model is pretty mechanical, meaning that you follow the rules and there is pretty much one way ahead. It's a one-way traffic. Okay? Yes?
Is there a way in the ER diagram to show, or does it show by implication that there's only one instance of or one record for the employee working for the department?
Well, if your design is the one on top, that automatically implies, yes, because by this argument, you can only have one line, one relationship connecting the same two entities from one same relationship set. Okay? But that's an excellent question, all right? Okay, that said, we end up with this design right here. So employee works in a particular department, and the primary key of this table, obviously is a combination of social security number and department ID, because that uniquely identifies a line, which is a relationship. In other words, a record in the instance of this table. Each of this line, so each of this little dots, become a record in the employee table. Each of the little dot here become a record in the department table. Each of the line here become a record in the instance for the works in table. And you identify that record by looking at the combination of the keys of the two participating entities. In other words, in this case, social security number and department ID. And here comes your foreign key, right? Here comes your foreign key. Because you cannot borrow, quote unquote, borrow the keys from the employee and department table respectively in the formation of your works in table. So you end up with two foreign keys. One is social security number, That's the foreign key references back to the employee table, and the other is the department ID. That's the foreign key references back to the department table, where they are the primary keys of employee and department table respectively. Okay? Any questions regarding this? Yes?
Oh, so what's the best way to do inheritance from ER to tables? Like if there was like a person entity, then the employee was inherited from that.
Oh, you mean the hierarchy structure?
Yeah, can we tie the primary key of that one to through I was very confused how to keep the inheritance there while also keeping the primary keys.
Well, you're talking about hierarchy structure, which I will talk about that in a minute.
Oh,
okay. So just stay tuned. Okay, bear with me a little bit. Okay, go ahead.
Are we allowed to change the names of the table?
You can. Yes, you can. You can have different names for a table than those from your ER design, but it's best, as I said, the best is to keep them the same name so that for yourself and for others checking your design know what's going on, which is mapping to
From the relational set to the entity sets.
Yes.
Like, say they need different.
It goes both ways, right? I mean, if I look at your ER design, look at your relational table design, if you have the same naming conventions, obviously it helps for me to quickly understand your design, right? Obviously.
Are we allowed to change foreign key names?
Yes, you are allowed to change foreign key names as long as you make it clear which table it references back, so that even if you have a different name here than the name of this attribute in its home table, I still know this actually is your primary key of the other table. You can even be, in some database systems, it allows you to be explicit, right? Because when you say DID references department, what happens if department has multiple keys? It's not clear whether you're referencing back to the primary key or one of the candidate keys. Does that make sense to you guys? So in some database system, it allows you to not only references the table, but also the attribute name from that table you reference back to. Then there's no ambiguity whatsoever, right? And it's super clear which key you're linking back to as your front key. All right, so that's many-to-many. That's the simple, trivial case to capture. What about the more involved case? What about the more involved case? Basically, this boils down to what I have drawn on the whiteboard, right? If you have this mapping constraints, what about one-to-many, many-to-one, one-to-one? How do we convert those to relational tables? First of all, a simple observation is whether it's one-to-many or many-to-one or one-to-one, all of this can be considered as a special case of many-to-many, right? Because if you have many-to-many, you have covered all these special cases. So that means that the trivial naive solution is to treat all of this, one-to-many, one-to-one, simply as many-to-many. In other words, whenever you say one-to-many, many-to-one, one-to-one, you still treat them as kind of like many-to-many, which means you produce a table for that relationship set and borrow the keys from the two participating entities and also add whatever relationship set specific attributes to the relational table you adopt, regardless whether it's many-to-many or one-to-many or one-to-one. But the observation, which I'm going to mention next, will save you. But one observation is that doing this will introduce an additional table for the relationship set. And obviously, intuitively speaking, you do not want to have way many two tables in your design. Okay? Less number of tables means a cleaner design. And later on in our discussion, you will realize, now it's too early to explain the reason behind that, but later on you will realize smaller set of table leads to better query efficiency because you're going to do less number of joins. Join is the operation of kind of glue two tables back together, which is really expensive. So you want to try to cut the number of joins you want to do in SQL queries, and one way of doing that is to reduce the number of tables you have. Okay, so intuitively, you want to reduce the number of tables in your design as much as possible. So, how do we? Why that discussion, which is reducing number of tables, have a connection with this mapping constraint? Okay, which I'm gonna explain next. Okay. So let's try to look at this example again. But I'm going to change this to a one-to-many mapping. So employee manage department. And we talked about this relationship that before. A department may have, which is one employee. They manage multiple departments, and a department may have only one manager, right? So one-to-many map. You follow me? That's a one-to-many map. By the way, one-to-many and many-to-one, obviously they are the same. They are symmetric, right? If you know how to handle one-to-many, you should be able to figure out how to handle many-to-one. Okay, so if I draw this out on the whiteboard, what's going on here? Well, what's going on is as follows, right? This is my employee, this is my department. So one employee may manage multiple departments. So my setup may look like this. Sorry. So it's the one-to-many, right? So a department may only have one manager. So that line should not exist. So I may have a setup like this. And I have no total participation constraint on both ends. So I may have some employees who are not manager at all. I may have a department who doesn't have a manager. That's totally okay. But in this case, every department happens to have a manager. That's okay as well. Okay? So the important thing to note is that you cannot have that second line, which I have just erased. This line is not supposed to exist. Why? Because of the one-to-many mapping constraint you have. Do all of you follow me? Okay. Excellent. So we're going to erase this line. So the next discussion actually brings up the key point I want to get over. I want you to try to understand, right? So in many mapping relationships, what we said to identify this line, you need to look at the two participating entities. So the keys of those two participating entities will be good enough to identify that line. The same statement obviously still holds. To identify this line, you look at the employee ID and department ID. Identify this line, you look at the employee social security number and department ID, so on and so forth. But you can do better. How do you identify this line? Knowing that each department can only have one manager, which tells you there will be only one line connecting to that department. So how do you identify this line? Well, all you need is the department ID itself, plus the corresponding manager information. The key observation is if I expand, imagine this is whatever this dot represents all the attributes you have for the department. I'm going to simply expand this a little bit with the social security number of that department's manager. Let's say this is social security number 1. So all I need is to add social security number 1 to this entity, and I will be able to identify not only this entity itself, but also this managed relationship set attached to that entity. You follow me? So how do I identify this entity and that line? I just do that. What about this? Okay? That's all I need to do. So this way, I do not have to introduce another table for the relationship set. All I need to do is to expand the entities on the department side with the key of the department's manager. You may wonder, okay, why don't we go back and do the same? Let me finish the discussion and answer your question. You may wonder, why don't we do the same trick for this as well? Okay, let's try to do that experiment over here. You know, if we try to do the same for a many-to-many mapping, what happens? Well, keep in mind, now because it's a many-to-many, every entity here may be attached to multiple relationships. So if you try to do that, you will have SSN1, SSN2 for the first entity, and SSN1, SSN3, and SSN4 for this entity. And you may have SSN2 for this entity. And what's the problem you notice on here? It's no longer structured. It's no longer structured. Why is it no longer structured? Because you cannot have a unified schema to describe these entities anymore. A unified schema means that regardless what are the records in my instance, I have the same schema at top. But in this case, you no longer can do that because every entity have slightly different structures. That slightly different structure lies in the different number of employees who work for that employee. So you can no longer have a unified schema to describe all the entities or all records going to this table or this entity set. Does that make sense to you? Simply put, how many SSN attributes I should have for the schema of the department? You don't know, because it depends on the actual instance you have, which may change over time. And that goes against the very basic principle of structured data design, which is regardless of the instance you have, the structure of your data stays the same. Right? That's the structure, that's the fundamental principle you need to hold, you need to uphold in a relational database system, in a structured relational database system. Right? So for many-to-many, this does not work. But why it works for one-to-many? Well, the keyword is one. You only have one mapping from the other side. So I know for all the instances you have here, I just need to have one social security number. It's fixed. It's fixed. Okay? That's why I can do this. Question mark.
But couldn't, okay, if you just look off of the diagram as it's drawn up there, wouldn't that necessarily introduce, or could introduce null values, because the departments, we haven't specified, because it's not a bold line, so there could be, it's 0 or 1.
Yes, excellent observation. So that's actually the next topic I'm going to discuss. This design get rid of a table which is, so I no longer need to capture this table, right? But because of that, there's no free lunch, right? What's the trade-off? The trade-off is you're going to introduce a social security number attribute to the department table that was not there in the first place. Okay? When you convert the department entity set to the department relational table. But because you have to introduce this now, what's the problem? The problem is if a department has a manager, fantastic. You get rid of table, you store the manager social security number here. Perfect. Clean, nice, succinct design. What about a department that does not have a manager? Let me add a department to illustrate that. Then this department is forced to have an attribute that's not necessary in the first place. If you go with a design like this, That wouldn't be a problem because I simply do not have to store that department ID in this table. There's no redundancy. Now this keyword will show up later on. Redundancy. And there's a saying, later on, I will reinforce this concept. Redundancy is the evil of database. Redundancy is the evil of database systems. Okay? Redundancy is the evil of database system. Later on, you will realize and appreciate this statement. Yeah, question?
What if there was some sort of attribute in between employee and department?
If you have an attribute here as date, you simply copy them over as well. And that works because you know you only have one line going into this entity, so there will be only one such value per this entity. So if you simply copy over that attribute over, it will work. Okay? Now going back to this redundancy problem, right? For a department that does not have a manager, yes, you have to introduce a null value for it. So you're wasting some space compared to the design where you have a table by itself for a one-to-many mapping. Let me finish, then I'll answer your question. But the benefit, what's the benefit? The benefit is, suppose I ask you to answer a query like, who is the manager for department A? Who is the manager for department A? I also want to know the name of the department and the budget of the department. Okay? Not only I want to know the manager SSN of department A, I also want to print out other information for the department. You follow me? With this design, what you have to do? Well, you have to look at this table first, find out the department ID, department A, the social security number of the manager for the department A. But you're not done yet because I'm asking for additional information for that department, which is not available in this table. Which means what you have to do, you have to go back to the department table and do what we call a join. Between the two tables, a join will basically find the records that have matching values on the key and the foreign key constraints. Okay, have equal values on the key and the foreign key constraints. So all the records here with the same department ID, again here, will be matched together. And that allows you to find the social security number and additional attributes that goes in here for that department. And that's a join operation. And the cost of a join operation is expensive. Okay? Simply put, let's imagine you have two tables, each has n records. How do I find all the matching pairs from these two tables? What's the naive algorithm? Someone tell me here. So the problem is very simple. Okay? The problem is you have two tables, each has some attributes. Each has n attributes. N records, not attributes, n records. And I want to find the pair of records, one from each side, that have a matching value on some given attribute. In this case, department ID, right? What's the naive algorithm to solve this problem? Most straightforward algorithm to solve this problem.
Take each attribute from the top and compare, or take each one from the top and compare it to the one on the bottom and find the match.
Pairwise checking. Pairwise checking. Check every single pair. What's the cost of the algorithm, Daniel?
O of n squared.
Okay, that square is important, right? It's O(n) squared, right? Because the first record from the first table check against every single record on the second table. For each pair, you check whether the matching attributes have the same value or not. If they do, they survive the join. If they don't, throw away. Move on to the next pair. There are n square pairs to check. And now let's compare, keep that in mind. Now let's compare this design. What is the cost if I ask you to print out the department information and the manager SSN? Well, for the same task, what do I do? Well, I simply go through this table linearly, and for that, I simply print out every single record. And what's the cost of that?
reduce that to linear time. Because what you can do is go through the first table, store those values as a set, backed by a hash table or similar good data structure, and then you have to go through the second table once as well, but then you can check in constant time whether that member is equal to a number.
Suppose you have a good hash function that will work, and suppose you do equality join that will work. But what about general condition join? Not equality check. For example, I want to find out, for argument's sake, I want to print out the department and the manager information when the department ID is greater than some other department. Does that make sense to you? So it's no longer equality join. So his argument is excellent, by the way, which is something we will discuss later on, which is the efficiency of evaluating an SQL query. And in particular, how do you evaluate joins? Joins are expensive. As you can tell, 2 tables, in the worst case, n squared. For 3 tables, this becomes n cubed. For k tables, it becomes n to the power k, in the worst case. However, for typical equality join, when you check equality condition against some attribute, you can typically do better using what he described. If we formula that, is also known as hash join. You can use a hash join algorithm to do it efficiently. In most cases, suppose you have a good hash function. What do we mean by good hash function? I will talk about that later on. Right? But the basic point is it produces least amount of collisions when you hash your keys. You hash your keys. But what about general join condition when it's no longer equality conditions, arbitrary join condition? Then you no longer can apply that trick, and the only way you do it is to do this. In the worst case, it's n squared. It's n squared. Okay? Compared to this design, it's guaranteed to be linear time always. And if you have very few departments that have no manager for that department, then this redundancy issue is not a problem at all. Plus, it's a null value. Right? Plus, it's null value, meaning that this, again, later on we will talk about the design of a database system. The null value is, in general, easier to deal with than actual value, and it's less costly than actually storing a value in it. So the overall cost of this design is not that bad, unless you have a very sparse table, meaning that most of your department do not have a manager for that department. Then you will consider this design rather than this design. But if most of your department have a manager and very few do not have a manager, obviously this is a better approach. Does that make sense to you? Question?
Yes, this is easier design too. If we wanted to delete a department, then we didn't have a whole other table to check constraints and integrity on, right? So if we just wanted to delete a department, then we just delete a department. We don't have to go check another.
Well, you are referring to the reference to integrity constraint, which I skipped before we talk about the conversion from ER to relational, but that's an excellent point. She was referring to, let me repeat her question, she was referring to the foreign key. Once you have a foreign key, what happens if you delete a record in another table whose key happens to be a foreign key value for another table? For example, student register for classes, right? So what happens if I delete that student? Should I also delete all the information, which classes that student has registered for from the enrollment table? As for that, we are converting to relational model first, then we go back to those topics. But that's an excellent question, and we will come back to that point later on when we talk about that. Okay? So that's one-to-many mapping. Okay? So the rule of thumb to keep in mind, to recap the discussion we had. For one-to-many mapping, you do not produce, in general, you do not produce a table for the one-to-many mapping itself. Rather, you capture one-to-many mapping by taking the key from the one side and place the key into the many side. And along with that, you take all the attributes for that one-to-many mapping relationship set and place those attributes into the many side as well. So the key from the one side goes to the many side.
So in the ER diagram, the department side does not have SSN attribute.
No, this is strictly for converting to relational table. In the ER design does not change.
Okay.
Your ER design has nothing to do with how you produce your table here, right? So the reason you do not copy the key over to the department entity set in your ER design is because that's already captured by the fact that it's a one-to-many mapping constraint. But you need to somehow reflect this one-to-many mapping constraint in your relational table design. The way you reflect that is by taking the key from the one side and place into the many side. But this does not affect your ER design itself. Okay.
So if it was total participation and it was exactly one, you just make it part of the primary key?
Okay, that's an excellent question. That's something I'm going to discuss right next. Okay, what happens if you have total participation? What happens if you have total participation? Okay, let's go on to that. First of all, let me show you this design right here. So this is on the top is a many-to-many mapping constraint. Many-to-many mapping constraint. On the top, I shows you if you treat this as, even though it's one-to-many, but you still treat it as many-to-many mapping constraint, and you follow the discussion we said earlier, you simply convert that to a table by itself. So that will give you the managed table on the top. Right? That will give you the managed table on the top. But rather than doing that, what you simply do is to take the key and the attribute for that relation set, and take the key from the one side and place into the many side, you end up with the design at the bottom. You end up in the design at the bottom. Does that make sense to you? So on the top is if you treat this as a many-to-many mapping, and that will give you a table by itself. But for our discussion, since it's one-to-many mapping constraint, so we'll just go with this, which is taking the key from the one side, place that into the many side, and also the attribute of the one-to-many mapping relationship set, and place that into the many side as well. And you will have a single table like that. So you no longer need the table on top. You no longer need the table on top. Now let's look at participation constraint, which is Brandon's question. Okay? So if you have a participation constraint like we show here, employee managed department now at both this line, what does it mean? That basically means a department must have exactly one manager, right? Exactly one manager, right? This means department must have exactly one manager, but note that on the employee end, I do not have a both line, which means not every employee is a manager. You may have an employee who is not a manager, who does not participate in this managed relationship set. But every single department must participate in this managed relationship set. That's indicated by the both line, and the fact that there is only at most one manager if you do participate. Combining these two arguments, you arrive at each department has exactly one manager, right? So how do I capture that? Well, how do you capture that? Well, in our design, the way you capture that is to make sure, if we look at this example here, it's possible if you do not have total participation constraint, it's possible you have a department whose manager social security number is null value. Right? It's a null value. All I need to do is to ensure what? You cannot be null, right? So I enforce that this is not null. That's all I need to do. And this is another reason why, in this particular case, having this one-to-many mapping as by simply adding additional attribute to the department table is better than creating a table by itself, because enforcing this constraint is much simpler. All you do in SQL is to enforce that social security number is not null. And this, later on, we'll have a formal discussion on this, but for now, just remember this. This is what we call a column constraint. A column constraint is a Boolean expression you introduce after a column. which specify a constraint that column must satisfy. Example. In another example, age, check. Example age. That's another column constraint. Okay? Meaning the age value must be at least 18 years old. Okay? Do you follow me? So that's what we call a column constraint, right? Yeah.
Is there any advantages to having it be a column constraint instead of making it part of the primary key of the table?
Okay. Part of the primary, well, by making this part of the primary key, you mean primary key. Are you referring to this?
Yeah.
Okay.
And then it would also be not null.
So there is a significant difference among the two, okay? In this design, every department record can appear only once because the primary key is still DID. In this design, if you make primary key of this table as DID and SSN, what happens? Well, the same department record now may appear multiple times, as long as it is associated with different managers. And you actually break the one-to-many mapping constraint by doing that. By making DID and SSN as the primary key for this table, you are actually doing a many-to-many mapping. And even worse, you're doing this on the department table rather than a separate table. And what's the problem with that? Well, every single time you introduce an additional manager for that department, you need to duplicate all the information for that department another time. And that actually goes back to the reason why we need to have a separate table for many-to-many mapping rather than going with this design. Because if you do that, every time you have a new manager attached to a department, you need to duplicate that department attribute. All the department attributes, you need to duplicate that one more time. You follow me? That's actually an excellent question. Do all of you follow Brandon's question? Cool. All right. So for this part on delete no action, let's ignore this for now. This goes back to her question earlier regarding enforcing referential integrity constraint. Okay, and you can ignore this for now. I will come back to this later on. So that's how you enforce total participation constraint. Imagine in this particular case, if you were to design this as a many-to-many mapping constraint and produce a separate table for it, it will be much harder to enforce this total participation constraint because what you need to check is every single department ID here must appear in this table right here. You follow me? In order to have this total participation constraint. And that's not something that's easy to check. We'll learn how to check that constraint later on. You need to use tools. You need to use the help of SQL to do that. But it's basically the bottom line is it will be way harder to enforce that total participation constraint compared to this approach. Okay. Speaking of which, if I have this many-to-many mapping constraint, I pull this up again, which is working, and I have a total participation constraint here. By our earlier discussion, this is many-to-many mapping, so what I do, I will produce a table for this many-to-many mapping constraint, right? I will produce a table for this. But the question is, how do I enforce this total participation constraint? What do you need to check? Well, you need to check every single social security number appear in that table, and every single department ID appear in that table. At least once. You may appear multiple times, that's okay, but you need to appear at least once. How do you do that? Well, the short answer is we cannot do that right now. Later on, we will learn tools such as a trigger and an assertion using SQL to help us achieve that objective. So this part is, we will defer the discussion on that until we learn more about SQL, and then we'll come back to that. Okay? Do you follow me? And simply using, you may wonder, what about I simply use this? Isn't this Doesn't this enforce this constraint, many-to-many constraint? The answer is no, it does not. All it tells you is every single record in that table must have SSN and DID value. But this is not the same as every single SSN value from the employee table must have appeared in this working table. These are totally two different things. Okay, so it does not work. Okay, so that's one-to-many mapping. What about many-to-one? Well, it's the same, symmetric, right? Now, what about one-to-one?
I have a question.
Yes.
Couldn't we possibly enforce the, like that minimum constraint by requiring that, say, the SSN and the employees table be a key in, or be in person? Sort of like.
By this design, what you said is already there. So SSN and DID, the combination of them is the key of this table, of the working table. But merely serving as a key, as part of the key, SSN itself is not the key of this table, by the way. The combination of them is the key of this table. But merely being part of the key of this table does not give you the fact that every single SSN value from this table must exist in this table here. It doesn't give you that. Right?
How do you implement a participation constraint in a many-to-many relationship?
How do you enforce this total participation? We will discuss that later on. Once we learn more about SQL, we need to use assertion and trigger for that purpose. Okay? So, lastly, what about one-to-one mapping? Well, for a one-to-one mapping, you can treat it as either a one-to-m or m-to-one mapping, meaning that you can take the key from one side and place into the other side. You can do it both ways. But you do not produce a table by itself for the one-to-one mapping. Okay? So I'm running short in time. I'm going to skip weak entity set because as far as homework 1 is concerned, we don't need this part. So I will, yes?
So for one-to-one, so do the keys appear at both at the same time?
No. You take one key from one side and place into the other side. Like treat it as a one-to-many.
So you can only
You can do it both ways though. For one-to-many, you take the key from the one side and place into the many side, but you never can take the key from the many side and place into the one side. If you do that, if you take the key from many side and place into one side, you run into the same problem. You don't know how many such attributes you may have on this side because it's many. Many could be 2, could be 3, could be 4. Does that make sense to you? So you can only take key from one side, place into the many side. And what I said for one-to-one is you can treat any one of the one table as the many and do this trick.
So what happens if you put it on both? Like you take the foreign key from this and put it on the other one, and then?
Well, then it's unnecessary for you to do that.
Okay.
Right? By taking key from one side and placing to the other one side, you have already captured this relationship. Why you want to do additional?
But that way you can enforce that it's one-to-one.
I think we can take this offline. Okay. All right. Now let's look at the hierarchy structure. This is part of your homework 1 problem. I actually give out this hint in discussion forum, but maybe some of you keep a close, pay close attention to what's going on in the discussion forum. So for problem 1 of your homework 1, we have a people entity set, which is all the people record in the healthcare database, and we need to distinguish male and female. And obviously, the best way to distinguish them is to have a people entity set as a parent entity set and male and female as 2 children entity sets using a hierarchy relationship, right? For that method. The question is, once you have a design like that, how do you convert that to a relational table design? Which I'm going to discuss next. So in this case, I have employees and I have hourly employee and contract employees. And how do we convert this to relational model heavily depends on what type of constraints you may have regarding this either hierarchy structure. So remember, we have overlap constraint and the powering constraint we talked about, right? Overlap constraint basically says do you have overlapping elements or overlapping entities from the hourly employee and the contract employees? The current constraint says if you take the union of hourly employee and the contract employee, does the union give you every employee in your parent entity set? So overlap constraint can be allowed or disallowed. Current constraint can be true or false. Okay? So how do you convert this to a relational model? Well, generally there are three approaches. There are two approaches. The first approach, which is obvious, right? You follow what we said earlier. Every entity set goes to a table by itself. So you have three entity sets in this case, even though they have a special relationship, which is parent and children entity set. I don't care, I convert each one of them into a relational table. The parent entity set, that's clear, that's a standard entity set. You convert that to a relational table. But what about the two children entity sets? Well, the point is, you take the key from the parent entity set and use them as a key for your children entity set. Furthermore, what about those attributes from parent entity set? Do you capture those attributes in the children entity set, in the three-table approach? The answer is no. The reason for that is by taking the key from the parent entity set and placing that key into the children entity set, you are able to link a children entity to its parent entity, in which you can retrieve the values of those common attributes from the parent entity set. In other words, you do not have to copy those attributes from the parent entity set to the table set. Does that make sense? So you will have three tables here. The first table will be SSN. That's a three-table approach. What about the two-table approach? Well, if your covering constraint is true, your covering constraint is true. If that's the case, then you can use a two-table approach. Because by covering constraint is true, knowing that fact, what do you know? You know every entity, every employee entity is either a hourly employee entity or contract employee entity. There's no other possible scenarios. So if I just produce two tables, I will be able to capture all my employees. Does that make sense? So when that constraint is true, you can still go with the three-table approach, but alternatively, you can go with the two-table approach by having an hourly employee table and a contract employee table only, without the employee table. And when you do that, this time around, you do need to copy the attributes from the parent entity set into the children entity set tables. In other words, your two table will be SSN name lot, hourly wage, hourly work, and the other table will be SSN name lot and contract ID.
So, for example, if you went with the two-table approach,
yes,
and the key, social security number, was a foreign key in another table.
You are talking about two-table approach?
Yeah.
So in two-table approach, there are no. In two-table approach, there will be no foreign key. In the three-table approach, yes, that's a foreign key in the other table, in the parent. For the two-table approach, you don't. The other thing is, what about overlapping constraint? If you go with two-table constraint, if you go with two-table approach, if you go with two-table approach, this is a subtle issue, right? All you need is covering constraint to be true, covering all the employees. The overlapping constraint, how do you handle that? If you go with two-table approach, since you have copied the attributes down to the tables for the children entity set, if you do have overlapping constraints set to allowed, meaning that an employee could be a contract employee and an hourly employee at the same time, if you go with a two-table approach, what happens? Well, you have some degree of redundancy. That same employee will appear in both tables. So the name and lot and SSN information for that employee will be duplicated twice. You follow me? So the point is, if you have many such overlapping entities, your best choice is still go back, even if covering constraint is true, your best choice is still go back to the three-table approach to get rid of that redundancy. If this redundancy is minimal, meaning very few employees are in this category, then a two-table approach will be fine. Yes, you have some degree of redundancy, but this degree of redundancy is very minimal.
So it seems like though too maybe you'd want to go with the three-table approach. And, I don't know, whatever application you're writing for some reason, most of the time just operates on employees, and then there's just like a couple little harebrained things that do.
In that case, obviously you go with three-table approach. Yes.
Okay, because otherwise you always have to deal with those two tables if you want to interact with employees.
Yes.
Right?
So from efficiency, you're talking about from efficiency point of view. If there are cases where, regardless of the concern on efficiency, you have to go with three-table approach. For example, current constraint is not true, then your only choice is to go with three-table approach. But when you do have a choice between three tables and two tables, it boils down to efficiency and redundancy, the trade-off between the two. Yes.
Would you please explain the two-table approach again?
If current constraint is true, meaning that every employee is either a contract employee or hourly employee, then you don't have to keep an employee table by itself.
I understand that, but what does it look like? I mean, is it?
You will have contract employee and hourly employee taking down all the attributes from the parent entity set. In other words, your two table will be SSN name lot, hourly wage, hourly work. That's the first table. SSN name lot, contract ID. That's the second table. You simply take all the attributes down to the tables for your children entity set. One last comment I'd like to make. When you go with the three-table approach, it is possible to introduce relationship set between a child entity set and the parent entity set. I'll give you a concrete example. In your homework 1, problem 1, you have a person entity set as a parent entity set. You have female and male, and you are required to capture this biological father and mother relationship. And obviously, biological father and mother speaking, if that's your objective, obviously only a male can be a biological father. Only a female can be a biological mother. Does that make sense to you? So in order to capture that, you would introduce a relationship set between male and person and female and person. That obviously should be a one-to-many mapping as well, because yes, you can have multiple child, but every single child can only have one mother or one father. Biologically speaking, right? Things become so complicated nowadays, right? So, but that's why I use the keyword biological father mother. You only have one biological father, right? In most cases that I have heard of. Right? Rare case does happen. You can Google it. Okay, so that summarizes my discussion on ER converted to relation model. I give you some nice picture representations of the discussion so far. ER to relation model, well, an entity set goes to a table. The key of your table is the key of your entity set. Many-to-many mapping. Mapping, I ignore the tables for the entity set, right? So these two goes to two tables respectively, following convention 1. The relationship set itself goes to a table itself. Does that make sense? What about one-to-many? You could have, for our discussion earlier, you could have a table for the one-to-many relationship set itself, but that's not encouraged in practice because you want to reduce the number of tables you have. So rather than having that, you ignore R1. Rather, you add the key and attribute of the relationship set. You add the key from the one side plus attribute for the relationship set. All of this goes to the many side, to the table for the many side. So in this case, E1 is your one side, E2 is your many side. So for the table correspond to E2, so the E2 table will have all its own attributes plus the key from the one side plus all the attributes to the relationship set. Does that make sense? So the complete picture is this. For many-to-many, you have three tables, E1, E2, and R1. One-to-many, you have two tables, E1 and E2. The many table is expanded by the key from the one side plus attributes for the relationship set. And many-to-one is symmetric. And one-to-one, you can treat it as either one-to-many or many-to-one. So here comes the weak entity set. I think I do have time to talk about this. So the general point is you treat it as a one-to-many mapping. So it's basically the same as this. Does that make sense? The basic point is that. The only difference is what's the key for the E2 table? What's the key for the E2 table? In the one-to-many mapping case, for a normal entity set, the key for the E2 table will be the key of E2 itself. So simply the key of E2 itself. But because it's a weak entity set, it's always identified, if you recall the discussion we had on weak entity set, right? An entity in the weak entity set is always identified by its owner entity. Right? It's always identified by its owner entity. That implies the keys for the table of a weak entity set should be what? Should be the combination of its key of its owner entity plus its own key, right? So the key for the weak entity table will be the combination of the key of the weak entity and its owner entity, its identifying owner entity. Okay? And the rest is the same as the one-to-many mapping. For a hierarchical structure like this, you have two choices. Choice number 2, method 2, is only available to you if covering constraint is true. But even when covering constraint is true, you still can go with method 1, which is three-table approach. What about ternary relationship set? Well, for a many-to-many ternary relationship set, the conversion rule is the same as what we have discussed for the binary relationship set. Each participating entity set goes to a table itself, and the relationship set itself will produce a table, where the attribute of this table will be two parts. One is the keys of all participating entities. You grab all the keys. The combination of those become the primary key of this table. And in addition to that, you will have the attribute of that relationship set that goes to this table as well. So that's the design from as shown here. Okay? The reason for this is clear. By taking all three keys for the three participating entities, you can uniquely identify the line connecting the three entities. Together with, of course, additional attributes attached to that line. That form your table, right? So the same kind of argument here. What about aggregation? Well, for E1, R2, E2, and E3, you do the same as before. Okay, I still have 1 minute. Meaning for that binary relationship set and those two entity sets participating in that binary relationship set, you do the same conversion as we discussed before. Entity set goes to a table, many-to-many. If it's a many-to-many mapping, that goes to a table by itself. If it's a one-to-many mapping, you take the key from the one side, place to the many side. This part stays the same, no change. The question is, how do you capture this relationship set right here? By the way, E3 is a normal entity set, so it goes to a table by itself, no change. The only change, the only special case is how do you handle this relationship set right there? Well, you can kind of think that relationship set, the aggregation of that, as a super entity set. Okay? And how do you identify an entity or instance from that super entity set? Well, it is the key of the two participating entities from E1 and E2 respectively. Right? And now you have a relationship from E3 to that, which is E1 and E2, the keys of E1, E2. So in order to uniquely identify that, this is the same as kind of like a ternary relationship set. You simply take the key from E3 and the two keys of the participating entities for E1, E2, and R1, and altogether that forms the key for this aggregation relationship set. So an aggregation relationship set will give you a table by itself, and the keys, the primary key of this table is simply the key of E3 and the combination of keys on the E1 and E2. Of course, with additional attributes attached to that relationship, like E1 to DJ, as shown here. One last question before I
Yeah, so
stop today.
so there will be 3 keys.
No, 3 keys from 3 tables, but the combination of them is a single key, single primary key for the aggregation relationship table. With that, I stop right here. I'll see you on Wednesday. Okay? Yes, I do.